Hey, welcome guys. Welcome to my analysis video. So today let's using the power series technique, the previous power series technique to get to give the definition of exponential and the log function. Okay, so actually you can use this power series technique to define the exponential and log function, and you can define the trigonometric function. So you can view this is the analysis video, the analysis definition for all these special function. So let's define e of z to be zn and factorial from 0 to infinity, and then you can use the ratio test to prove that the converger radius will be infinity. So wherever z you will converge, and the key property is this one. You can compute a product of two spatial two of these, and yeah, and prove this to be this. And minus n and n factorial minus n factorial. Okay, and you just pull out this one, and this coefficient, right, can be written as in terms of the the binomial coefficient, and the z of, sorry, this is let's say change k, which you can change this using n from 0 to n, and to n z zm or wn minus m. So you can easily see this it's just this. Okay, so only this step is non-trivial, right? And then you use binomial coefficient and pull out this, you get this, and then you get this. Okay, so one consequence is that ez e minus z. So remember that what we just get the first property of this function, which is ez plus w. Right, so if you put w into minus z, you get ez, which is e, z minus z, which is just e of 0. And then by the property of power series, e of 0 is 1. Okay. Okay, moreover, that's you can prove the derivative. Okay, by the way, so this property, right, this property shows that the e of z is non-zero for all z. Okay, and also by definition, e of x is greater than 0 when x greater than 0. Okay, and also e of, obviously that e of x goes to infinity as x goes to infinity. Yeah, so basically this is just what you think is an exponential function. So basically all the properties can be derived using the power series. Okay. And yeah, that's talking about the differentiation. So you can ask this. Okay, but this is just a by property of what we prove, it's just this. Okay, so you can pull out the e of z and only ask about h goes to 0, e of h minus minus 1 divided by h. Okay, and at least you can easily compute, right? Because it's just derivative differentiation respect to 0. So you can just use the power series, right? So you get 1. Okay, so basically you just prove this. Okay, and so now I can define the natural log e to be defined to be e of 1. Very stupid, right? But I just define e to be this. And then you can see my I have a previous video that I have a video proof that if you define e to be this, then you can easily prove that e is irrational by using this property. Okay, and since it's e of z1 up to zn, it's just e of z1 at e of zn, right? So you can easily say that e of n, when n is positive integer, is defined is just e of n, and then you can easily define e of negative n, and then you can easily define e of p divided by q. You can easily compute p divided by q when this is rationals. Okay, and finally, you can define x of y to be the sup of x of p if y is irrational. Sorry, if y is irrational, and where p is less than y and p is rational, and you can use this and see that this e of z is actually exponential z that you are really familiar with some exponential functions. Okay. So basically, this is just a property that you can recover. From your analysis. From your common sense. Yeah, so I think I don't want to keep talking about this because I think this is simple. And you can also define. So now one can define log functions. Okay. By the previous, hopefully by the previous one, you'll know that exponential x is strictly increasing. Okay, the reason is that its derivative is just this, right? So by the mean value theorem, if you have f of x minus f of y, there exists the c such that f prime of c x minus y, right? So but now this guy is always positive. So it means when x greater than y, your f of x is greater than f of y. So e of x is strictly increasing. Okay, so you can maybe plot as this, and you know its infinity is infinity, and the negative infinity is 0. Okay, so now you can define log as the inverse function. So yeah, because it's, and you see it's in strictly increasing, so it's 1-to-1 from a real number, right? So you can define inverse. So you can define inverse e of ly to be y. So ly is the inverse of exponential x. Okay, so notice that the e of ly is y, and the L of e of x, which is x, right? This is y greater than 0. This is x is real. But because exponential is always can be defined for any real number, right? So actually for any complex number, and the exponential x, and you take the log, it become x, right? And then for the log, you only define positive number, right? Because your images can only be positive. Okay, and then you can do the differentiation on this side. And then you get L prime of e of x, e prime of x to be x, or to be 1, right? Just do a differentiation respect to x. But this guy is just e of x, right? So you get L prime of e of x, just 1 over e of x, which you gain that L prime of y is just 1 over y. So you can view, you can imagine that your Ly just log y. So we just use this property and prove that the standard differentiation of the log y will give you 1 over y. And by using e of 0 is 1, then you know that L of 1 will be 0. So by the fundamental theorem of calculus, your L of y minus L of 1 is just y1 dy divided by y, right? So this is the fundamental theorem of calculus, and you know L1 is 0. So basically, you just prove the definition. So this is your calculus definition of log y. So one definition of log y is using this, but now we are trying to go into a reverse way to define. Once we define exponential x, we define the log function as the inverse function of the exponential x. Okay, and then you can prove basically, yeah. So now now if I define L of y to be as the inverse function of exponential x, then you can, or e of x, then you can use this definition to show that this guy is just actually the log where you're familiar with. And I think I don't have to prove this, so yeah, just prove by yourself. Okay, so now let me just go to the trigonometric function. Okay, so one can actually define a cosine and sine, right, via exponential x. Yeah, so one or e of x, if you want to use a power series, you can use e of x. Right, so one definition of cosine e of x is defined to be half of e of ix plus e of negative ix. And the sine of x to be 1 over 2i e of ix minus e of minus ix. Okay, and obviously that the e of ix will be cosine plus I sine. So okay. Yeah, so actually, I mean, one can just believe that cosine and sine just using this exponential this is just somehow like the analytical way to using a power series of exponential x to define cosine and sine. And obviously that by definition, you can see the property that you are familiar with. Cosine 0 is 1, sine 0 is 0. Hey, by the way, I use C and S just to camouflage so that you don't think this is cosine sine. So now you need to think it's a power series of exponential. Okay, now you can easily see that C prime of x cosine differentiation is sine. So this is also come from the property of this exponential x, right? Because we know that e prime of x is just e of x. And the sine prime of x will be minus cosine of x. Okay, so now here comes the amazing part. So amazing part is that we can show. So we can show that there exists a positive number, let's say x, such that the cosine x is 0. Okay, so this is very amazing that there's no periodic when I define exponential x. But if I plug I in it, we will automatically come out with this cosine sine, both will be periodic. But how can we use the analysis to show this fact? Okay, so let's prove this. So I want to prove that there is a positive number x such that cosine of x is 0 or c of x is 0. Okay, so the reason is the reason goes follows. So we know that the c of 0 is 1. Okay. Okay. And let me just prove by contradiction. So suppose c of x is non-zero for all x, right? But c of x is continuous, right? C of x is continuous. So if it's non-zero, then it must be always greater than 0. There's a case that it can be less than 0, but c of 0 is 1, right? So now your c of x is 0 is 1, and you guarantee that it's always non-zero, right? So it can immediately become this, right? It cannot be, so it always can be, it must be positive when x greater than 0. Okay. Okay, so now c of x will be s prime of x by the right. So that means s prime of x is greater than 0 for all x greater than 0. So this means that the sine, this s function will be strictly increasing. Okay, but I know that s of 0 is 0. Okay, so that s of x will greater than 0 because s will strictly increasing. Okay, so now let's consider 0 less than x less than y, and I have x y minus x, well less than y of x as of t, right? Because s is strictly increasing. So if I integrate x to y, then it will greater than s of x y minus x, and then this is just a c of y minus c of x. Also c of y minus c x minus c of y, right? Because cosine is differentiation is negative sign, right? So this is c of x minus c of y. Okay, but the problem is that the problem is what? The problem is what? The problem is what? The problem is that, okay, so now let's see what we arrive, right? So we arrive at s of x y minus x is less than c of x minus c of y for s less than for x greater than 0 and less than y. But remember that we have e of ix modulo square, which is e of ix, e of negative ix, which should become 1. So that you get e of ix is 1, right? So which you can start here and see that you can start here and see that c of x greater less or equal to 1. Okay, and also when x is real, right? By definition, because your c of x is exponential x minus exponential plus exponential ix plus exponential negative ix, and then when you prove each term is modulo can at most 1, then c of x is less or equal to 1, and also s of x is less or equal to 1, but it's violate this, right? Because y can be arbitrarily large, right? So if you fix x, which is non-zero, and y be arbitrarily large, then left-hand side will become infinity. But right-hand side so can only be bounded by 2, right? So there is a contradiction. Okay, so that means there is this x zeros such that the c of x zeros is 0, right? So the first term which cosine goes to 0 is pi over 2, right? But actually, I mean, I guess that you're not, yeah, I mean, okay. Okay, so one can define pi. So this is the very weird. So you can define pi to be 2x zeros. Yeah, so I can define x. Oh, I should define. I should be the s to be the smallest positive integer. Oh, sorry, the smallest positive number, such that the cosine x0 is 0. And this is just from your perspective, pi over 2, right? So I can define pi to be 2x zeros. So this is very interesting that you can define pi to be using the analytical way, but using the cosine, the first 0 of cosine. By the theorem that you prove that cosine must be 0, and you see everything is automatically one by one follows, right? So even though you don't know about your original definition of a trigonometric function, then you can still get most of get these properties. Yeah, so this is so weird. Okay. Okay, moreover, so if you know c of pi divided by 2 is 0, so now I define pi to be 2x 0. So it's just definition. And then you can see that s pi over 2 or plus or minus 1. But you know that c of x is greater than 0, right? So you can get that s is increasing as 0 pi over 2. So you get s pi over 2 is 1. Okay, then you get e of pi I divided by 2 is I. So this is your common results. And then you also get like e of pi I is minus 1 because you square it. And the e of 2 pi I is 1, right? So basically you show that the e has periodic 2 pi. Okay, so this is very weird that you get something you're familiar with. And e of z plus 2 pi I will be e of z. Okay, so the following. So we have the following. The first one is that e is periodic. So this exponential is periodic with with period 2 pi I. And the second is that c and s, cosine and sine, are periodic with 2 pi. Okay, so this is actually all these need to be proved, right? Because now I define cosine and sine with this exponential x, all come from the power series. And the c is that if t less or equal to t belong this region, then e of it will be non-1. Okay, and also d, pick a complex number which is modulo is 1. There exists a unique t from 0 to pi such that exponential t will be z. Sorry, it to be z. Okay, so basically EIT. Okay, so basically now I want to prove all of these things. Okay, so proof. Okay, so I think yeah, so this is the so I think I don't have to prove these two, right? Because it comes from definition. come from my definition of pi. Okay, so I only need to prove C and D. Okay, so suppose we have got this, and the E of IT is x plus IY, which is xy are real, and you can show that exponential for IT will be x to the 4 minus 6x squared plus y squared, y squared y to the 4th plus 4i xy x squared minus y squared. Okay, so suppose E for IT is real. Oh, by the way, let's assume that the x is from 0, 1 and y is from 0, 1. Okay, suppose this guy is real, which tell you that x squared must be equal to y squared. And we know that the x squared plus y squared must be 1, right? This is what we already showed that the EIT is always 1 by the property of the power series. And you can easily solve this, right? You only get the right. You get this, right? You can easily solve x squared equals y squared, and then x squared y squared is 1, so you get x squared is half, right? Y squared is half. Okay, so you get the exponential for IT will be minus 1. Okay, so which proves this? Okay. Now let's prove D. Right, so for D, let's consider this. And I know that exponential IT2 minus exponential IT1 minus 1 will be exponential IT2 times exponential minus IT1. So by definition, you get exponential IT2 minus T1 or IT2 minus IT1, which is non-zero by C. Okay, so C tell you that in this region, which can be non-1, right? Non-1. So which tell you that the D is uniqueness, the uniqueness of D. Right, but in this just tell you that this is uniqueness, because their difference cannot be 1, right? So that means D is different. If T exists, then it must be unique. Okay, so we still need the existence. Okay, so let's say we fix Z to be 1. And let's write Z to be x plus IY, and also x and y are both real. Yeah, I mean the proof is a little bit lengthy, but it's a little bit stupid. So you can define x as suppose, right? Suppose x is greater than 0, y is greater than 0. That means on a 0 and to pi over 2, you know that C decrease, right? So that means C of T can be x for some T. Then also you know that C, the cosine square plus sine square is 1. And S is greater or equal to 0 because now S corresponding to Y. So you just pick that T, right? So Z to be exponential IT. And then you can, yeah, this is just the first quadrant, and you can consider the rest of quadrants easy to prove. It's a little bit stupid, so I don't want to prove it. Okay. Okay, so what this mentions that by the previous 1, 2, 3, 4, you know that if I define gamma of IT to be exponential IT or exponential IT, where T from 0 to 2 pi, then gamma of T, right? Because gamma of T will not intercept itself, right? So gamma of T will be a simple closed curve. Right? Who cares? It's just a circle. Right? Okay, and easy to, and by the previous results, you know that the EIT is 1. So your gamma of T dt 0 to 2 pi will be 2 pi. Okay, that's it. Yeah, this is just a common, this is just all the properties of the trigonometric function and exponential function all come from the power series. Okay, so that's it. So next time we talk about some algebraic complex of the complex field. And that's defined, that's close off. And then we talk about Fourier series. Okay, see you.